Hi everyone, this is Professor Fernandez, and in this video we are talking about Module 1 in Lesson 16. So I'm going to scroll up really quickly actually just to mention a few things about the lesson as a whole. This is a capstone lesson in the course and also in the Unit 4 that we're in. By that I mean that we will be using concepts and definitions and results that we've sort of accumulated throughout the entire course. We're going to be extending line integrals to the setting where the integrand involves a vector field. So that's going to go back to lesson 13. And later on, we'll be talking about Green's theorem, which relates line integrals to double integrals. So we're going even further before that. And then we'll be revisiting the notions of curl and divergence that we talked about in the previous lesson, which of course are defined in terms of dot products and cross products. So there's a lot going on in this lesson as a whole. So I encourage you to perhaps take a look at the videos a few times to have a chance to slow down and digest everything that's said. I also encourage you to read through this multivariable calculus in the real world snippet. This will give you a sense of where circulation and flux might pop up in the real world. So I want to go back to the first module in the lesson here and start telling you a story about how the first big notion in this lesson came up. So this is the notion of a vector line integral. So the first thing I'm going to do is take you back to physics and particularly the notion of work. I'm not going to say too much about this. I'll say just enough that we need to motivate the new concept. But this is a math course, not a physics course, and I don't expect you to have any sort of physics content knowledge to begin with. But in a very simplified setting, suppose that this is a box and you are trying to move this box. Slide it across a distance d in this horizontal direction. We can already think a little bit using vectors how this might go. Suppose you apply a force F on this box and you actually set it into motion. It's not too heavy of a box, for example. And you do manage to move it this distance d along the horizontal direction. So there's a basic notion in physics of something called work. And, it means something slightly different from the word that it means if you just think of, going to work, for example, if you're doing a job or something. In physics, this means the force that is applied over some distance to an object that causes motion. So that right there could be a little confusing. Suppose this box is really heavy and you try your hardest. You're pushing really hard but it doesn't move. According to the physics definition of work, the distance you move the box is 0, so you would have done no work on the box. Again, that may not, line up with our notion of doing work. You certainly pushed as hard as you could. Your muscles were working, but not in the sense of this definition. So in a physics sense, a force does work if it actually moves an object over some distance. And then the actual work, according to this physics notion, that's done is the magnitude of the force multiplied by the distance the force moved the object over. So this is in the simplest setting where you have this force. It's in the same direction as the motion. So what if we go over here and we switch things up a little bit, and rather than imagining there's a very light box that you can move very easily, maybe it's a slightly heavier box. And you decide instead to push it, instead of pushing it, you decide to, maybe tie a rope onto it and pull it. So this is more of the situation you might imagine, where now, you might be up here trying to pull, this is my terrible rendition of you, up here trying to pull this rope attached to the box. So what would happen? Well, mathematically, the force that's being applied is not totally in the direction of motion. Some component of it is, this x component is in the direction of motion. This component is not in the direction of motion. I'm assuming here that you're not lifting the box off the ground. So some portion of that force contributes to the notion of work in the physics perspective done, but not all of that force. So how would we generalize this force times distance? Well, we would say the horizontal component, here's the force F. The force F can be decomposed into this horizontal component, Fx, and this vertical component, Fy. We know from all the work that we've done that because I'm assuming this F is applied at an angle theta with respect to the horizontal, then the horizontal component is the magnitude of F times cosine of theta. you can see it effectively being popping out of this right triangle here, that fx is length of the hypotenuse times cosine of theta. Okay, so then we would say that in this case, the work done is magnitude of f times cosine of theta, and then we're still moving it across a distance d, so that would be d here. But I can think of d as a vector, as I'm doing over here, and this would be then magnitude of f times cosine of theta times magnitude of the d vector. So you can already see that if I move things around here, something that is familiar should start emerging. So this is exactly the dot product of the force vector with the distance vector. So this is a slightly more general expression that tells us how to calculate work done by a force F in the case when F and D are not exactly in the same direction as they were over here, force times distance. So now what I'm going to do is I'm going to use this concept, and I'm going to take us out of moving boxes around, and I'm going to make things a little bit more abstract. So that's the picture over here. Suppose that I have a vector field now, so I'm not thinking of you or me moving boxes, but I'm thinking about maybe you're standing outside and you're feeling the wind rushing around. So I'm just drawing a few of the vectors here, f of the vector field here in red. And suppose that I consider a curve C here, this black curve, and imagine, for example, that this curve, let's make it like a string, and maybe it has a little bead on it. And this bead, therefore, is going to get moved around the curve in different directions at different speeds by this wind field, this vector field. So the question is, what is the quantity that expresses the work done by this wind field on this bead as it moves along this curve C? So to set that up, we're going to do something very similar to what we were just doing, except now we're adding some of the multivariable calculus concepts in here. So I'm going to start, for example, at this particular point along the curve, and I'm going to assume that I parametrize the curve using an r of t, so that point corresponds to r of t for some time. And then I'm going to say, a little bit later, at t plus delta t, let's say that the force, the velocity field, has moved the small bead over here. You can see that that's pretty much what this velocity vector field would do, because this velocity vector has a component that goes along the curve, and it has a component that goes perpendicular to the curve. So the component along the curve is going to move the bead to the right, which is along the, which will eventually get it over here to this point. Okay, so suppose that at time t plus delta t, that is where the bead ends up. And then what I'm going to do now is I'm going to try to use these two blue vectors that determine the initial and final points of the bead along the curve to tell me what the displacement was, what the change in position was. So that's this picture down here. So notice up here that, if I do my vector, go back to my vector properties of arithmetic, right? If this is r of t and this is r of t plus delta t, then if I do this minus that, right, I'm getting the vector that points in this direction. So that's what I'm drawing over here. So that's r of t plus delta t minus r of t. That is what I'm going to call delta r, and that's this blue vector here. So now effectively we can kind of think of this as if we're back in the box picture that we just talked about. We now have a force F that is being applied over some displacement, some distance, delta r, and we can think about the work that is done by the force, by this vector field in moving the bead over that displacement. So that would be this quantity. And I'm calling it delta W because I'm thinking of this as a small change in the work quantity that we're going to calculate soon. And therefore, if I looked at the entire vector field over this entire curve C, not just this little snippet of it, I would be adding up all these little additional quantities of work that the vector field would be doing to move the bead across the curve. So that would get me over here. This effectively is a Riemann sum of f dot delta r. If I think now of this change in r as being infinitesimally small, so instead of being a delta r, I think of it as dr, then the work done I could think of as infinitesimally small, a dw. And therefore the Riemann sum would, in this infinitesimal limit, convert to an integral. It's not just any old line integral because we're doing everything along this curve C. So it ends up being a line integral because we're going along the curve, and the curve could be not straight. So this is effectively the motivation that we get to for what we're going to mention in a minute is a vector line integral. And I'll do that in a second, but first let me go back very quickly and show you another notation that we're going to see in this definition that I'll review in a minute. Remember that delta r here is this difference, r of t plus delta t minus r of t. If I divide both sides by delta t, then I get delta r over delta t. And if I take the limit as delta t goes to 0, this tends to dr dt, becomes r prime of t. So from here I can see that dr as a quantity is the derivative r prime of t times dt. That is useful because then I can go over here to this new vector line integral we've defined, and I can replace that with r prime of t delta t dt. Great, and then I can do one more thing. I can say, well, what if I divide by the norm of r prime and multiply by the norm of r prime? I'm not changing the equation. If I do that, then this might trigger also some other concepts that we talked about earlier in the course. This quantity, r prime divided by r prime, that is the unit tangent vector. And this quantity over here, norm of r prime times dt, remember that was what ds was, the infinitesimal change in arc length that we had talked about in lesson 13. In other words, this new quantity that we have just motivated and defined, this vector line integral, could have this form. It could also have this form. They're equivalent forms. One of them effectively parametrizes with respect to t, right? This becomes that. The other one parametrizes with respect to arc length s. So that's really the difference. In both cases, the takeaway that I want you to have here is that there's some vector field, and what you're asking is, if I draw a curve, how does that vector field push around particles, objects, beads along that curve? And the notion from physics that becomes useful is the notion of work. I'm looking only at the portion of these vector fields that push around these beads along the tangent, right, along the tangential part of it. For now, we're not concerned about what the vector field does orthogonal to the curve. That will come later. Great, so at this point we have said enough so that we can go through this definition. So let's talk about it. So this one says, let C be a smooth curve parametrized by r of t, where t is between a and b. Suppose f is a continuous vector field defined on C. Great. The line integral of f along C is defined as exactly what we just motivated. So integral of f dot dr, which becomes f dot t ds, that was this up here. And then just as a comment of how you would evaluate this, we'll do an example in a minute. The vector field f depends on x and y through its components. So you would use the parameterization, which is telling you x of t, y of t. Substitute that in for the components wherever you see x and y, respectively. And then do the dot product of that with the derivative of r. So I've written that out mathematically here. Here's your vector field, components f and g. Here's your parameterization. So this dot product is literally plug in your x and y, their parameterizations for f and g. And then when you do the dot product, you multiply by the derivative of x, that's x prime, and the derivative of y here, that's y prime. Then you add them. That's the dot product step. And then, this is now taking us back to the types of integrals we were solving in lesson 13, the scalar line integrals. It's technically two integrals, although we will often, as we did there, just write one integral. So it's this integral plus that integral. So you notice as I write here that, back in lesson 13, we had some useful interpretations of the scalar line integrals when they were parametrized by arc length. That was the whole area of the curtain thing that I talked about in that lesson. We had a little trouble interpreting what the integrals meant when we had dx's and dy's. So now we see that, integral of f dot dr reduces to, this is dx, this is dy, reduces to exactly integrals of that type, line integrals of that type. In other words, what I say down here, calculating vector line integrals reduces to calculating scalar line integrals, and specifically the ones that involve these coordinate line integrals, dx and dy. So this is what I say here in the second note. We now have some nice meaning to line integrals of this type, even when the f and g functions involve a z, because that effectively just means that the vector field has a third component. So there is a way now to give meaning to the line integrals in lesson 13 that we could not give meaning to before, if we think of them as connected to some vector field whose components are f and g and h if there's a third component. Okay, so that's pretty much all I want to say about this general definition. So now let's go off and try to calculate some of these line integrals and talk about what they might mean. So in this example it says, let C be a unit circle centered at the origin, traced out counterclockwise, and then evaluate this vector line integral for these two vector fields. Great. We're using the same C for both of these, so let's just parametrize C once and for all, so then we can use it for these two calculations. So C is a unit circle centered at the origin, and we've parametrized this a few times now. We can write R of t as cosine of t and sine of t. It's traced out counterclockwise and only once, so that tells us that t goes between 0 and 2 pi. Great, so extracting the x of t and the y of t from there, we get x is cosine and y is sine. And then I'm going to need the derivatives, so x prime is minus sine and y prime is cosine. All right, and then now let's go off and calculate the vector line integral of this first vector field. So I'm going to have minus y comma x times dr. Dr is dx dy. Okay, so I'm just kind of writing everything out here so we can review how this actually works out, but we actually don't need to do all these steps. If I scroll back up, this is really what we're going to end up calculating anyway, but I'm writing out all the steps to review them. So over here I get minus y dx plus x dy. And we can see that this is where I need the information from the derivatives that I calculated. So dx is, well, let me substitute in what y is first. So y is sine of t, so this is minus sine of t. And then dx is x prime times dt. X prime times dt. And then x over here is cosine t. Cosine of t. And then dy is y prime of t times dt. Cosine t dt. Everything is now in terms of t. T ranges from 0 to 2 pi, so those are my limits, 0 to 2 pi. And then now I simplify. Here I get sine squared. Here I get cosine squared. I'm adding them, and I know sine squared plus cosine squared is 1, so I get integral from 0 to 2 pi of 1 dt. And that just becomes 2 pi. Okay, so for number 1, I'm going to say answer, because I'll have to erase this to give myself room. Answer is 2 pi. So in other words, if we were thinking about this vector field, and we plotted this vector field, and then we drew this unit circle, and we looked at the work done by the field in moving, this fictitious particle around this curve once, the answer would be 2 pi. I could give you units, but they're not going to mean much because I don't have other units in the problem. But I've plotted the vector field here that we're dealing with. This is the same one we saw in the previous lesson. And so you can see if I drew any curve here, let's keep it in blue, any circular curve here around the origin. This is the unit circle of radius 1. And I imagined a bead on this circle, then the vector field vectors really do push around this bead, and they do some work in doing so, right? There's some energy expended to do that. And we've calculated that energy to be 2 pi, again, ignoring the units. So that's just a very, very quick and rough idea of what is going on and what we're measuring. Okay, so let's try this again for the second vector field here. So I'm just going to erase, I'm going to keep the parameterization the same. That's what is implied in the problem. And I will go back and erase things as they need erasing so that I can keep some of this writing here. So the vector field is 2x, 2y. So that goes over here, 2x and 2y. And then, so I'm integrating slightly different things now. So I have a 2x and a 2y. First thing I'll do is I'll pull out the 2 because that's common to both. And then here, basically what's different is what these first terms are. Dx is still x prime times dt, so that's this term. Dy is still y prime times dt, so that's this term. Those don't change. What changes is 2x and 2y. So now I have x, which is cosine of t, and then I have y, which is also cosine of t, so that's over here. Oh, sorry, that was y prime. So y is sine of t, which is over here. And then now we recalculate. So notice that this is negative cosine times sine, and this is plus cosine times sine. So I get 0. And therefore, my integral is 0. So the answer for number 2, answer is 0. Okay, so what could that mean? Well, so I have plotted here the vector field. This is the field 2x, 2y. This one on the left, remember, was the field negative y and x. So when I drew the unit circle here, we did see, just based on the picture, that if we pretended there was a bead here, these vector field arrows really were pushing the bead around and doing some work in the physics sense, generating motion across some distance. If I draw a circle here, the unit circle, you can see what's happening, which is that all of the vectors are everywhere perpendicular to this unit circle. So if I place a bead on the circle, like right here, and then I ask, is it going to move? The answer is no, because no portion of the vectors here are ever tangent to this circle. So there's no force, if you will, being applied tangent to the circle to move the bead along the circle. Instead, all the force being applied is orthogonal to the circle. So, the bead can only quote-unquote move that way or this way. The vector field is moving radially outward, so the bead is not going to move because I'm restricting it to move only along this unit circle. We will later on consider what happens. We're throwing away effectively all of the motion perpendicular to our curve. We're only looking at, again, as we said earlier, motion tangent to the curve. But, there is something to be said about the fact that this vector field is pushing only outward and does not yield motion along the curve. But again, we'll get to that later on. For now, this explains why this integral is 0. This vector field, despite, there's a bunch of vectors everywhere, for the particular curve we've drawn, does not generate any motion along this curve. No work is done. Okay, so that's this example. So now I want to go back to, broaden our horizons here and start thinking about why did we get a 0 here, no work, and why did we get a non-zero here, a positive number specifically. And, you might have remembered from the previous lesson, this is the same vector field, the same two of these actually that I've been using from the previous lesson. This one was conservative, is conservative. So this is the gradient of a function f, where f of xy is x squared plus y squared. This is a conservative vector field. So you might start thinking at this point, maybe conservative vector fields have something to do with a zero work integral, maybe there's a connection there. And that's another thing that I'm doing to plant the seed in your mind, and those answers will come later in this lesson. But I do want to, as an intermediate step to getting to that answer, use that as a springboard to now talk about conservative vector fields and vector line integrals, specifically the path independence association there. So here is a theorem. Suppose f is a conservative vector field. Again, it's the gradient of some function, which we call the potential function f. And suppose this vector field is defined on some open domain in R2. Again, we're talking about vector fields with 2 components. You could generalize this to 3 components, but we'll keep things simple for now. Let C be any piecewise smooth oriented curve with initial point A and B. Remember, piecewise smooth means that C could look like this, and then like that, and then like that. These are all piecewise smooth curves. And oriented means that we have some notion of, the curve, not just this. I have an orientation either that way or that way, right? So I have some notion of orientation. Great. And then initial point A and B, this is where the curve starts, and this is where the curve ends. That's just initial and terminal point. Okay, then, finally, the conclusion. The vector line integral f dot dr over C is equal to f of b minus f of a. So this does not seem that important, perhaps, to be a theorem, because it almost seems like it's a fundamental theorem of calculus. And in fact, it kind of is the fundamental theorem of calculus in disguise, because if I write out the left-hand side, the fact that f is the gradient tells me that the integral of the derivative of little f is little f evaluated from b to a. So I do want you to think of this as what we were doing back in Calculus 1. Integral of f prime of x dx equals f of b minus f of a. In that sense, this theorem is the direct analog of the fundamental theorem of calculus to the setting of line integrals. So, what's new is the line integral. What's not necessarily new is the theorem, because there's such a direct correspondence. Nonetheless, I did want to include the proof here and just talk through it really quickly, because again, it reviews many of the concepts we've talked about in this course. The curve C, we're going to assume is parametrized by x of t, y of t, where t is between a and b. In the theorem, there's an assumption that the initial point is capital A. So capital A must be the x and y value coordinates for t equals a, right? The start of this curve. And then the terminal point is denoted by b. So that must be x of little b, y of little b, because b is the last t value. Okay. So at this point, we are going to then calculate the derivative of little f, the potential function. And we're going to use the multivariable chain rule. So little f is a function here. There we go up there. That depends on x and y. And x and y depend on t via the parameterization. So we've got to use a chain rule. So to calculate df dt, we do partial f partial x dx dt plus partial g partial y dy dt. And then we notice that, hey, this part is the gradient. There we go. And this part is the derivative of the parameterization. Great. So now df dt is the dot product of the gradient with r prime. And because the vector field is conservative, then the gradient equals the vector field. So that gets us here. And now we go back finally to looking at the vector line integral. We then have this f dot dr. Remember that was equal to this expansion of it. So going back to our definition, right? This comes from what we talked about a few minutes ago. F dot dr turns into that when you have the parameterization. Great. And then, well, here's f dot r prime dt, and there is f dot r prime. So f dot r prime is the derivative of the function f. Again, we plugged in the parameterization, so x and y in f of x, y get replaced by x of t, y of t. And now we're back to single variable calculus, literally, because this is a single variable function of t integrated over t from a to b, and it happens to be the derivative. We know it's the derivative of some function, namely f. So we're back to single variable calculus in that the integral of the derivative is the function. And then we plug in for t equals b first, and that gives us x of b, y of b. Subtract, plug in for t equals a, gives us x of a, y of a. And this x of b, y of b is what we called point A. X of b, y of b is what we called point B. So that gives us f of capital B. And then this point was what we called point A. That gives us f of capital A. Okay, so that is a run-through of the proof of this theorem. Again, uses a lot of the nice results that we've accumulated throughout the course, and also some stuff, of course, from Calculus 1. What is the meaning of this theorem? What does it signify? Why is it important? Well, notice that C here in the theorem is any piecewise smooth oriented curve with initial points A and B. So this is why it's called path-independent vector line integrals. So what this theorem is saying is that if you pick an initial point and a terminal point, and the vector field f and the curve C satisfies all these requirements, then any curve that you draw between A and B, doesn't matter how crazy, it doesn't matter how wiggly, any curve you draw, here I would calculate along this curve a certain vector line integral. Oops, sorry. And then I would calculate across the second curve another vector line integral, and then another one, and another one. What this theorem tells us is that they will all equal, all those 4 line integrals and all the other ones will equal the same thing. The difference in the outputs of the potential function at B and at A. In other words, it doesn't matter what path you choose to get from A to B. All that matters is the value of the function, the potential function at B, and the value of the potential function at A. So in that sense, it's very reminiscent, again, of the fundamental theorem of calculus, the f of b minus f of a, that just depends literally on the endpoints of the domain A and B. All right, so let me show you that as an example here. Suppose we have a vector field given by this, and you're told that it's conservative with this potential function. Somewhere down the road, you may want to verify that by taking the gradient of little f and getting capital F, but you're given that information here. It says evaluate this vector line integral where C is the simple curve from here to here. Okay. By the way, simple here means the curve does not intersect itself. So, this is not a simple curve, whereas this is a simple curve. So, it's that usage of the word simple, and not simple as in, straightforward or not complicated. Okay, so to do this, again, you might think, oh, I have to take this curve, I have to parameterize it, then I have to extract x, y, and z, got to find the derivatives, and then follow all these recipes. But the answer is nope. As long as the curve and the vector field satisfy the hypotheses here, then you can just use the theorem, and the vector line integral will equal the difference in the potential function at initial and terminal points. So let's see then if everything is satisfying the hypotheses, so we can use this theorem. So let's check. We have a conservative vector field. Yes, we do, we're told, with a potential function f. Great. Defined on an open domain D. We're not told what the domain is, but this is all of these components and this function itself are continuous, differentiable everywhere. So we can take whatever domain we'd like. C, the curve has to be piecewise smooth and oriented. So this is a point, this is a point. So the curve, quote unquote, between these 2 points, again, you could pick any curve, but we can think of it as a line segment. C is any curve. It has an initial point, it has a terminal point, so we're done with all the hypothesis checking, and we can now actually apply the result. So what is the result? The result is that integral over C of f dot dr equals f of b minus f of a. Great. And so we're doing f of the final point, 1, 2, 3, minus f of the initial points, -3, -2, -1. And then this is our function here. So we're doing 1 squared times 2 minus 1 times 3 squared plus 2 times y times z. And then we're subtracting -3 squared times y minus x times z squared plus 2 times y times z. Okay, so this is just a bunch of arithmetic to calculate. So we have 2 minus 9 plus 12, and then minus over here we have 9 times -2, that's -18. Let's see, plus 3, and then we have plus 4. Okay, so I've been known to make silly errors, especially most mathematicians actually, because we spend so much time thinking not in terms of numbers but in terms of other mathematical objects, make silly arithmetic mistakes. So I actually won't try to simplify this. I may have already made such a silly mistake in the last few calculations, but we'll say that I'm going to get some number here, and that number is literally the answer for the vector line integral in this problem. There is no need to even parametrize this curve, right? Because I could have parametrized it as a line segment between those two. I could have parametrized it as a quarter circular arc. It really does not matter, because based on my theorem, any piecewise smooth oriented curve yields the same exact result. So I don't even have to find a parameterization. The default parameterization, between 2 points is a line segment. So we could certainly say that, let C be the line segment between these 2 points. And we could write down the parameterization, but we don't want to do that because we don't want to actually parameterize and then calculate the vector line integral that way. We want to use our theorem. So again, this is a really, really nice theorem, independence of path. This is true when f is a conservative vector field, and we will see this theorem reoccur later on in this lesson. The last thing that I'll mention, this is down here where we're going to talk about the next module, flux and circulation. The last thing I'll mention is that I really do encourage you to go back to this first part where we were talking here about the motivation for vector line integrals, and maybe spend some time making sure that this definition is clear, because this is a notion that is going to recur in the next 2 modules in this lesson, and certainly further down the road if you keep going with multivariable calculus. You'll see these vector line integrals pop up in lots of different places. And this is the lesson and the module where you can say, I saw this here first, but I also want to make sure that you understand it at a fairly deep level in terms of at least what we've said, so that it anchors your understanding going forward. Great, so that's it for this lesson, and I'll see you in the next